So we have like, all right.
If you're going to be down,
Get started soon. Wait for. How are you doing today? Nice. Thanks so much for joining our very first self-based systems meetup. I'm Qian, one of the organizers. I'm also a co-founder at DBoss, and also another co-organizer is here, Alex, who stands behind in the back. Hey. So, who are we? We are system nerds. So originally we decided to start this self-based systems because Alex, me, and Ingjun actually met at SF Systems Meetup. And we were complaining about how far the commute was. It took me 2 hours to drive to San Francisco from Sunnyvale. So thinking that we want a bit more like accessible meetup for people in the South Bay area. And of course, we have our friends in San Francisco, so we can have a nice balance. Like some people will do commutes on this way, other people will do commute on the other way. So we're basically a group of nonprofit, independent system nerds who organize this talk series. And we had a first casual coffee chat like a month ago, and I recognize some of the faces. Thanks for joining that. So we plan to do a lot more like tech talks and also coffee chats in the future, especially this self-based systems talks are not affiliated to any companies or products. So we're just like, we're independent people who are organizing this. We plan to do it kind of monthly or bi-monthly depending on the schedule and depending on the venue of this. And we focus on systems programming, and for systems, it's a very broad definition of it. So it comes to our next slide. So actually we're looking for talks. So we're looking for engineering talks, not product pitches. So if you're interested in giving a talk, please scan the QR code here and submit your talk proposal, like your talk title and abstract. We welcome any area related to systems, including networking, systems at scale, like top-level application, how to scale application, how to scale databases, how to run the compiler, and then down to security, hardware verification, and testing, stuff like that. I will share the QR code and the link after the talk. And then we're also looking for venues and sponsors because we are a nonprofit. So we really appreciate Yugabyte for hosting this event. It's really helpful. It's such a nice office, and thanks for sponsoring us pizzas and drinks and providing a great environment for us to talk to each other. And so if you have a large office that can have a large space for 50 plus people, 50, 100 people, or if you want to sponsor some like drinks, coffee, pizzas, please talk to us. And the goal is to really like create a safe space for systems practitioners to talk to each other, know each other, and create a nice community in the South Bay area. And we are very inclusive, so if you're from San Francisco, welcome to join us as well. Or if you're from anywhere else. So. And let's get to today's talk. Thanks, John, for agreeing to give us a talk. John is a professor at Stanford, and you may know him for a lot of things, including the author of Philosophy of Software Design. I saw some people brought their book today. And John also co-invented Raft, the consensus protocol, log structure file systems, and John's the creator of Tickle TK, pronounced correctly. And John also worked on low latency databases, large scale systems, and today John will talk about networking. So welcome, John.
First of all, thank you everybody for coming to a talk that is not going to have any material on AI. This would be an excellent time to deplane. Let's see if I can figure out how to share my screen. Slides, yes, okay. Great. So today I'd like to talk about network transport protocols, the data center, and what I believe is the need for a new protocol. So first of all, I want to say TCP is a really astounding engineering achievement. It's amazing that this protocol that was designed about 50 years ago, when there were maybe a few dozen hosts on the internet with the total bandwidth less than 1,000th of that of your individual laptops today, the total internet bandwidth. And it has survived 50 years through so many technology changes and changes. It's an astounding engineering feat. But that said, when TCP was designed, there were no data centers. Even a dream anybody had at the time. And so as we look at TCP today, essentially every aspect of its design is wrong. So what I want to do today is to talk about that, explain what are the problems with TCP, and then what would a good protocol for the data center look like. And by the way, I have a candidate for that. It's a protocol called Homa that was originally created by a PhD student at Stanford, Ben Montessori, is his PhD dissertation. And then talk a little bit about how even Homa is better. Is there any way to actually bring it into widespread usage? And what are the challenges with that? So that's a quick outline of the talk. If there's one takeaway from all of this is that, particularly in data center networks, load balancing is absolutely essential. You need to spread the load out. That's important both in the hardware and in the software. And many of the problems with TCP happen to interfere with load balancing. That's one of the biggest problems with TCP. It's very difficult to do load balancing effectively with it. Okay, so first, what are the goals for data center transport? There are three performance goals. The first, most obvious one is you want high data throughput. That is, when you're sending really big things, they ought to be able to get transmitted at full speed of the length that you have. So this is a problem that's been around forever. This predates data centers. This is probably the driving problem that TCP has faced over the years. And actually, by this metric, TCP does pretty well. But then there are a couple of additional requirements that come about really only in data centers. The first one is that in data centers, the data center networking hardware is really pretty amazing technology, combination of throughput and latency. Within a data center, it's possible to do round trip times in less than 10 microseconds with today's networks. And so we'd like for the transport protocol to make that performance available to applications. We'll get close to it at least. And then the third requirement, also unique to data centers, and this is the one, I think most people know about throughput and latency, but there's another one in data centers, which is message throughput, not data throughput. By that I mean, you need the ability to send very large numbers of small messages. This is at the heart of applications that try and aggregate a lot of resources in the data center, things like broadcast or shuffles that you use when you're trying to have a bunch of machines working very closely together. Again, the networks allow you easily, you could send 10 to 100 million short messages per second from one machine. Your NIC, can transmit that many messages. Can your transport protocol actually do that many from user level? No, it's off 1 to 2 orders of magnitude. So these are the three goals, and again, in order of difficulty, so they go from least difficult on the left side to most difficult on the right side. But ideally, transport protocol would make all three of these things possible. Well, by the way, stop me with questions and comments along the way. Don't hold them to the end. As soon as the urge hits you, if you want to insult my mother, it's fine. Get that out of the way right away. Don't need to hold that until the end of the talk. Okay, so in order to do those things, so those main requirements, those imply some additional things you have to do. The first one is you absolutely have to be able to balance the load across multiple cores. The problem we face today is that network bandwidths are increasing at this amazing rate, literally exponential improvements in bandwidth. But CPU cycle times have not increased in about 20 years, and they're not likely to go up much in the future. And so that creates more and more pressure. The imbalance between the network speed and the CPU speeds is only getting worse. And my rough estimate is if you're doing mixed workloads, one core can manage maybe about 10 gigabits per second of load. If you're doing very large bulk messages, maybe it can do a little bit more than that. But that means if you're going to drive a 100 gigabit network, bidirectional, you need 10 to 20 cores just doing network transport. And the problem with load balancing is that if you don't get it just right, if you don't really spread the load evenly, then you end up with hotspots. We have a disproportionate part of the load, and that wrecks your performance. Drives up tail latency and also can affect throughput as well. So the challenge is how can you do load balancing in a way that doesn't create a lot of hotspots? Then the second implied requirement is in order to do this, we need to manage congestion in the network. Congestion in the network is when packets build up in queues and various switches, and when that happens, then that can cause, well, slows everything down. So congestion in the network occurs in two places. It can occur in the core fabric or out of the edge. So in the core, I would argue, in fact, this problem should be avoidable. It should be possible to do load balancing such that the core of the network does not experience anything other than short transient congestion. There's no long-term congestion. But if you don't do that, if you don't do the load balancing right, then that's going to hurt both latency and throughput. For example, if you have two flows that don't share hosts, one flow from A to B and one host flow from C to D, and they happen to somehow get routed through a single link in the core of the network, they can't both go at full speed. They're going to slow down because they're sharing that link. Okay, so that's the first problem. And the second problem is at the edge, that is from the top of rack switches down to the hosts. Here, we can't prevent congestion because if a whole bunch of machines all start transmitting to the same target, fundamentally, they can send faster than that last downlink can transmit the data to the machine. So that will happen. And there we need to manage that in the transport. Because if you don't manage it, then again, the buildup of buffers increases latencies for everybody. Okay, so a couple of these are not ends in themselves, but we have to solve these problems in order to get performance. All right, so now let's talk about TCP. So I've listed 5 properties here that I think are basically the 5 key things that make TCP what it is. Every one of these is wrong for the data set. 5 for 5 are wrong. So what I'm going to do in the next few slides is just walk through them one at a time and show you why each one of those is problematic. So first, the data model for TCP is a byte stream. So you have a socket, you push bytes in one end of the socket, they pop out the other end in the same order. You put them in. That's the fundamental data model. Unfortunately, that's not the right data model for most applications, and it causes a whole bunch of problems. I have 5 slides of problems just on the byte streams. The first one is that applications, they care about messages. You have some collection of messages, and so when you have this stream, well, you can serialize those messages into the stream, but the problem is that TCP does not know about message boundaries. There's no information about that. And so when the messages come out the other side, typically they come out in block-sized chunks, however big the receiver's buffer is, that's how many bytes you get. And it might have all of one message and part of another, or it might have parts of a message, it could have several messages in it. The message boundaries have been lost. And so that means that applications that want to do message-based stuff, they have to do message reassembly. Typically that means you just insert a length before each message so you know how many bytes to read for that message. This by itself is not a showstopper problem. It has a little bit of complexity, a little bit of overhead, but if that were the only consequence of the byte stream decision, that wouldn't be so bad. Unfortunately, that's not the only consequence. In fact, this is disastrous for load balancing. Now, suppose I have a stream that's very high throughput. That's what I'd like to have. Or a zillion messages coming to us. I'd like to spread those messages out over multiple threads on the other side for processing. You can't do that. Because as threads read from the stream, the messages are going to get all garbled. The thread gets, like this green message, ends up with bits and pieces of it going to all 3 threads in this example. It simply is, you cannot share one stream concurrently among multiple threads with TCP. It has to be read by a single thread at a time that can then read the lengths and reconstruct the messages. So that means, how do we do load balancing with this? Well, there's two approaches. They're both based on having multiple connections. One approach is you introduce a dispatcher thread, and all of the incoming connections for the whole application are read by that dispatcher thread. It reads the message length, fields out, it reassembles messages, and then it doesn't do any of the actual work. It then passes off messages to a collection of other worker threads, and they do all of the real work of processing that. This is the approach we used in the RAM cloud storage system. It was a research project that my students and I worked on for a while, a few years ago. The problem with this approach is two things. First, latency. Now every message has to pass first through a dispatcher thread, then over to a worker thread. That adds a half a microsecond to a microsecond latency. And then even worse, the dispatcher is a bottleneck. Every single message has to pass through that one dispatcher. And our experience is that you can do somewhere between 500,000 and 1 million messages per second, small messages per second. That's the most you can do in one thread. So that's not the 10 to 100 million messages that your NIC could actually sustain if you want. So not a very desirable solution. The other alternative is that you partition your connections. So you have a collection of worker threads, and when a new connection gets opened, you assign it to one of the worker threads, and it stays assigned to that thread for its whole lifetime. The problem with this is that it doesn't work very well for load balancing, because when connection is open, you don't really know how big of a load that connection is going to present, and it can vary over time. And so there could be a point in time when, say, the only connections that are active are the two connections going to this one thread over here. And so 2 of your 3 worker threads are idle, and one of them is overloaded. So it's really hard to do effective load balancing that way. And there are more problems with streams. The next problem is head-of-line blocking. If I have a bunch of messages that are all going to the same destination, so they're all going to go over the same stream, and there are some long messages and some short messages, you run the risk that the short message gets stuck behind the long messages, and so it gets really long latency because it has to wait for the long messages ahead of it to be transmitted. A theme you're going to hear over the course of the talk is ideally we'd like to prioritize short messages so they don't have to wait for long messages. But with streams, you're kind of stuck because they're the same stream. And then finally, the last problem with streams is that the reliability model is not a great reliability model. What's really going on underneath this is typically there's a request response protocol being implemented where a client sends a request to a server and wants to get a response back. And the reliability guarantee it would like is a round trip guarantee. So the client wants to know that my request was delivered, the server processed the request, and I get the response back. And if any of those things fail, I'd like to know about it. And the problem with streams is that they don't provide that guarantee. What the guarantee you get is a best effort delivery of either a request or a response, one stream. There's no sort of aggregate guarantees across all of this stuff. And actually, in many cases with TCP, if the server machine crashes, the client gets no indication back. It's just you launch this message and it goes off into the void and you never get a response back. So that means that in order to use TCP or any streaming protocol, the client ends up having to layer on additional timer mechanisms on top of this to detect failures and do retries if necessary. And that's just another source of complexity and inefficiency. And it's particularly annoying because TCP already has timers itself. It uses timers for doing retry on that stream, but it's not sort of doing the end-to-end timers that we need in order to get the reliability that the client wants. Okay, so these are the problems with the streaming model. Before I go on, any questions so far or comments?
Yeah, I'm thinking that with this model where you're splitting messages among different streams, then you might lose something in that, yeah, the next slide actually is perfect. Yeah, you might lose something in that if it was just one stream, you know that the red message comes before the blue message and the blue message comes before the green message. You have an ordering that's guaranteed that you know on the sender side, right? Is this a problem in practice? Is this something you thought about?
I see. That's actually a good question. That's going to come up again with Homa. So the question is, if we don't serialize these messages in that one stream, then they could finish out of order. Is that going to cause a problem for the application? But my belief is that in most cases, it doesn't matter. When an application issues requests in parallel, it typically doesn't depend on the order. And in the few cases where it does, it's relatively easy to impose an order later on. But if you're stuck in this, it's relatively uneasy to try and somehow make that short message get quicker. Other questions so far? Yeah.
So this makes sense, but if we were to take a step back and look at the entire TCP IP stack, maybe we could come up with configurations of Ethernet and IP, QoS, PFC kind of a thing, which could allow for the throughput to be okay across the entire stack, instead of just concentrating on TCP itself.
You're saying somehow if we don't just concentrate on TCP, but look at the entire stack, we can get rid of, and which problem is it you're thinking we'll get rid of if we do that?
So head of line blocking, for
Head of line
example,
blocking.
a buffer reduction. So
Are you thinking somehow you use multiple TCP streams in order to get rid of the
you
blocking?
could actually be doing QoS differently for different kinds of traffic, which would then go across different QoS streams in IP layer, or you could do it on Ethernet with PFCs, priority flow controls.
Suggesting things like you could use QoS maybe to provide sort of differential priorities among these.
Yeah.
Or,
Which I think is what
typically
we
that
could
stuff
do.
goes by the stream though, right? Typically the QoS is associated with the TCP socket as opposed to, because again, there's no, within a particular stream, there's no differentiation that some bytes are different from other bytes. They're all treated the same. And again, we don't have message boundaries, and so it would be very difficult to do that kind of prioritization.
Yeah, I give you message boundaries, but I think you could still do parallel connections, because that was one of the alternatives that we discussed, right? Partitioning of connections.
So
We could do
possibly
that.
you could do parallel connections to possibly ease this problem.
Yeah.
Although I'm going to come back and talk about why that will be problematic in a second.
Yeah, just to add to that, right? Like if you look at HTTP2 or so you would split the large message into small ones, into frames, and then you have a bunch of frames. Would that change things? It's still a problem.
Could you
still have,
split things into frames, and would that help? Well, again, the question is, are the frames all transmitted over the same stream?
yeah.
And so they have the same problem.
Yeah, I mean, it depends on the buffers you have on, like this is the fundamental thing we use in all our services, right? Like we still have, like you said, it's still a TCP level problem, but it probably doesn't show up as much as, say, between like a mobile phone and your service. There's a lot of move to quick, but inside the data center, if you use HTTP2, it kind of doesn't show up in practice. So I'm trying to understand.
Yeah, so
why.
I think what we are trying to say is TCP itself, this is a problem, completely understood, but if we were to like look at the entire stack, maybe some of these problems could be solved by making some configurations on application layer or downstream.
So the comment is, could you somehow at a higher level compensate for the deficiencies of the underlying TCP?
I think that's that's how TCP has
I
survived
think,
so long.
yeah, although I bet if we were to look at any one of those solutions, I bet we'd find ways in which that was not particularly satisfying, or it still had additional problems.
Okay.
One more question, then I'm going to go on.
Why data center? Like these are just TCP problem. It doesn't matter. It's data center.
Why data center? Why data center? So the reason for my interest in data center is because the way I got started is we were building a data center application. We wanted to get super low latency and high throughput and get all of these properties. Whereas over the wide area network, you can't get super low latency because you have speed of light delays. Okay. So I think data center, because it has this potential for low latency, that creates desires that are very hard to fulfill with TCP. If low latency is out of the question, then TCP maybe it's not such a bad protocol. Let me go on to the next problem. So the next problem is that TCP is connection oriented. That is, for each one of these streams, there's some state kept on both ends about that. That state is relatively long-lived, lives for the lifetime of the stream. And it's not small. In Linux, it's about 2,000 bytes, even if you don't count packet buffers, just the socket state. And the problem with this is that today in data centers, applications can easily have hundreds or thousands or perhaps even tens of thousands of connections. In the old world when TCP was first invented, You might have one or two streams open in an application, but we're not in Kansas anymore. So they have thousands of connections, and so that has become a problem. And people propose various solutions, like Facebook had a paper a few years ago on using proxies and pooling to try and share connections among multiple applications, because you could have many apps on the same machine. Each app could have thousands of connections open. And if you want to do NIC offloading, this is a mostly separate topic, but I believe eventually transports have to move to the NIC because we can't keep up in software. If you want to do NIC offloading, then again, this large amount of connections there, if you have thousands to tens of thousands of connections, each with thousands of bytes, that's a problem for the NIC. And so, for example, in the Mellanox NICs for many years, there was a serious problem with thrashing in the connection caches inside the NIC. That causes problems. Second problem with connections is that you have to set them up. So before you send any data, you have to pay the cost of setting up the connections. And in most systems, that's a non-trivial cost. Typically involves at least one round trip. Now, if you only have a few connections and they're open for a very long time, and you reuse them for a lot of data, then you don't care so much about the connection setup cost because you can amortize that cost over all the work you do. But in the data center, more and more we're going to these very small applications. If you have serverless or microserver environments where the service just doesn't live very long, and it's going to communicate with hundreds of other hosts while it lives, you can't amortize the cost of the connection setup. So you pay for that. That's a huge additional overhead. So when you go to serverless environments, having those connections set up is not a good idea. But at the same time, connections are kind of an article of faith in the networking community. You say, we shouldn't have connections. What do you do? No connections. How do you get reliable delivery? Flow control, congestion, you can't do all this. Well, that's the kind of the standard thinking, but actually you can get all these properties along with connections, and I'll talk a little bit about that coming up. But I think people have just assumed you have to have connections. And one of the things to take away from this talk is you don't need to make that assumption. Next problem, congestion control. And the issue here is if buffer queuing builds up in the network, you need to be able to detect that and slow down the rate of transmission in order to keep that under control. So how do you do that? Well, the classical way of doing that, which TCP and most protocols use, is to give that responsibility to the sender. So somehow the sending machine has to figure out that there's a problem and then cut back its transmission rate. But the sender actually has no direct way of measuring that. It gets all of its signals indirectly. And those signals today, they're all based on buffer occupancy. When queues start building in the switches, somehow the sender finds out about that. Historically, originally, the only way the sender would find out is if a queue filled up so much that it ran out of space and packets had to be dropped, and the sender would experience delays in getting acknowledgments back and would realize it would have to retransmit. That was originally. Today, there are various other mechanisms. The simplest one is called ECN, or congestion notification, or explicit congestion notification, where the switch monitors its queue length, and if the queue gets longer than a certain length for any one of its egress ports, it tags the packet with an ECN bit saying, looks like we've got some congestion. Eventually that information finds its way back to the sender, and the sender scales back. But the problem with these schemes is that you only find out about congestion once you've got a lot of buffers occupied. But it's too late by that point. And now you've got a lot of buffer occupancy, and now you're slowing everybody else down with these long queues. So it's just not a very effective way of doing congestion control. You're just guaranteed that you're going to have significant buffer occupancy. One of the ways I characterize TCP is like a heat-seeking missile that seeks out buffer space anywhere it can find it, and it puts packets in those buffers. It will fill every buffer it can possibly find if you don't do something to stop it. Questions or comments on any of these last couple of problems?
Are you talking about sender buffer or the buffer in the switches?
I'm talking about the buffers. The question is, I'm talking about sender buffers, the buffer in the switches. I'm talking primarily about buffers in the switches. Okay. And actually the biggest problem is at the downlinks. the downlink between a Tor and a host. That's the place where in-caps can cause the biggest vector buildup, but queuing can build up in the network fabric as well. Next problem, number 4 out of 5. How do you schedule? So if you have a whole bunch of flows or messages that need to be sent, how do you choose between them and how do you prioritize them? So TCP uses what's called fair scheduling. Like share the bandwidth across all of the active flows at a given time. So if we have, say, 3 flows with each with the same length of data to be sent, TCP will roughly interleave those. The problem with this is actually the worst possible approach. We're all the same. Because nobody finishes early. Nobody finishes until the very, very end, and then finally they all finish at almost exactly the same time. So it's not great. You're much better off doing what's called run to completion. Let somebody finish. Nobody benefits from being 90% done. You can't do any work until you have the whole message. So you're much better off, in this particular case, they're all the same size. Just pick one message and transmit that to completion, and then the next one, and the next one. Nobody does worse at this scale. The worst one has the same completion time as before, and 2 out of the 3 messages finish significantly faster. And while you're doing this, actually, we'd like to do even better than that. We'd like to actually use SRPT, shortest remaining processing time first. That is, send the shortest messages first, the ones that will finish the earliest, so we can get as many things finished as quickly as possible. Get the work finished so that the other side can work on it. But, of course, you can't do this if you don't have message sizes. TCP has no message sizes, so we can't do that. So fair scheduling is about the best that we can do. And oh, by the way, this fair scheduling is actually not fair. So let's take a look. This is from a performance graph we gathered on a cluster of 40 machines running. It was a synthetic workload trying to mirror sort of a representative data center workloads with messages of various sizes being sent between machines. And what the graph shows is for the different lengths of messages, that's the x-axis. The y-axis shows the latency. And the latency is graphed as P99 slowdown. So let me explain what that is. So rather than giving the actual latency, it gives slowdown. Slowdown is, you say, what's the fastest this message could be sent if you had an unloaded network and no congestion? And then how long did the message really take? And take the ratio. So that's the slowdown. So 1.0 would be perfect. You're running at optimal speed. And then P99 means we're looking at tail latency. So the 99th percentile worst slowdowns. And I'm showing, actually, TCP is the green curve, and the DC TCP variant, which has some improved congestion control in it, is the brown variant. So a couple of things you can notice here. First of all, the tail latencies are pretty bad. It's almost 100x slowdown for DC TCP and more than 100x slowdown for TCP. So a message that would normally take, say, 25 microsecond round trip for TCP now is taking multiple milliseconds, 2 or 3 milliseconds. Do a round trip. But the other thing is, it's not fair. If you look at the slowdowns for the short messages, they're significantly higher than the slowdown for the largest message. In fact, it's almost an order of magnitude difference. So the slow messages get punished. When your network gets loaded, you're running high load, you end up punishing the slow messages much, much, much more than the long messages. And it kind of makes sense because the long messages already take a long time. If they occasionally have to queue a little bit, it doesn't hurt them as much proportionally. Whereas those short messages, they take no time in the best case, and now they get stuck in these long queues that were created by the long messages. So TCP isn't actually fair, even though you can think of it as it's microscopically fair. Individual decisions, I feel like I'm giving equal weight, but the result is it ends up really prejudicing against the short messages. And then finally, the last problem. So the TCP, I'll say it expects, or the assumption is that packets will be delivered in order. So the packets will arrive in the same order they were sent. They will not reorder either in the network or in software. Now, technically, TCP doesn't require this. Actually, TCP has facilities where it can handle this some out-of-orderness in packets. But the problem is there are many other things in the ecosystem that depend on the ordering. In particular, a lot of performance optimizations based on batching assume that these batches arrive in a nice clean order. So the result is that in TCP, you have to try very, very hard to make sure that packets don't get reordered. And this just takes away all of the best opportunities for load balancing. And so the result is it guarantees you're going to have hotspots in both the networking hardware and in software, and that's going to kill your tail latency. And by the way, that explains the tail latency you saw in the previous graphs. It's all because of hotspots that are related to in-order delivery. So let me give a couple of examples. First one is in the network. So imagine we have a bunch of nodes sitting out here. We have, say, a 3-level data center network with the top of rack switches along the bottom, and then intermediate and top level switches. So a packet that goes from one node to another has to go up and then back down through this switching fabric. And in order to maintain ordering, all the packets in a flow have to follow the same path. So you pick a path for the first packet in the flow. Typically it's done by hashing on various header fields. And then all of the subsequent packets in that flow will follow the same path. So the problem is, what if some other flow, different source machine, different destination machines, there's no fundamental reason these flows need to have any links in common, but they just randomly each make their choices. It's all done independently. What if they happen to choose the same link here? Now suddenly you're going to get congestion on that link. Queues will build up. Any other, and by the way, if there happen to be any other like really short messages that end up taking that same link, now they're going to experience really heavy delays. And so because the choice of the links is randomized, the conflicts are inevitable. In fact, you will end up with overloaded links even when overall the fabric is underloaded at very, very low loads. You're still going to end up with these conflicts because the hashing mechanism will end up choosing the same links. So I believe that this factor, this flow consistent routing, is what explains essentially all of the core congestion that people experience in data center networks. Now I have that as a question mark here because I don't actually have measurements to prove that. I would love for somebody that actually runs a big data center to measure what's causing their core congestion. But I bet if you do that, my hypothesis is it's all because TCP demands that you route all of the packets in a flow consistently. If you could do packet spraying, where every packet took a different randomly computed path, I bet you see all of that congestion goes away.
Sorry, how does this relate to in-order delivery? I didn't catch the transition.
So in order to have guarantee, if you don't have all of the packets in a flow follow exactly the same path, they might reorder. Because there could be queues, if I send another packet over here, the queues might be shorter there, and you could get to the destination.
For this reason, you must decide a route.
That's right. Pick a single route that everybody follows.
Okay.
Basically, you have to guarantee sequentiality at every point. All the packets follow one after the other through exactly the same set of switches.
That's not a feature of TCP, right? I mean,
Pardon?
that's not a feature, that's not a guarantee that TCP gives, right?
The comment is that's not a guarantee that TCP gives. So again, TCP does not require that.
Right.
But in fact, if you want to get good performance, you have to do that because other things depend on it. For example, the TSO offload features in NICs, for example, depend on packets. If the packets are out of order, then it can't do automatic reassembly for you, and then the software overheads go up. So at various places in the system, people have built in this assumption that things happen in order. And so now everybody in the ecosystem knows we have to preserve that order.
It's an accidental.
Well, it's sort of accidental. I mean, there's some benefits from it, but then there's this portion of
Sounds
problem.
like abstraction leak. Sounds like abstraction leak, like
An
a
abstraction leak. I like that term. Yes.
like TCP is a high-level abstraction, but all the switches need to understand the details of TCP to ensure TCP performance well.
Other questions or comments?
So you mentioned that even when the fabric is not overloaded, you start seeing these congestions, right? Do you know at what percentage of load tail latency start, like let's say going 10x?
The question is, so what's the relationship between the fabric load and the additional latency that you see? So I don't have a good graph of that, but it's easy to see that you're going to get some interference. You can get even at very, very low, just because, again, randomly, if you have a lot of machines out there, the odds are, and a lot of connections open, odds are that a couple of those are going to coincide, that there'll be a couple of active connections that happen to use the same intermediate link, and now you're going to have all the congestion issues that creates. At the very least, it means they can't both run at full speed. All the links are the same speed, and they choose the same intermediate link. Now you have two of them. I'm only running at half speed, even though there's tons of bandwidth elsewhere in the fabric that could accommodate that. So the problem happens in hardware, but it also happens in software. If you look at the way packets are processed inside the Linux kernel, packet will typically traverse 3 cores over its lifetime. First, the NIC will assign it to a core that handles low-level driver functionality. And then it gets passed to a second core that executes the network stack, IP, TCP, IP Homa. And then finally, there's the application core, the core of the application is. And these cores are chosen by 3 completely independent schedulers. So the NIC picks the driver core by hashing all the fields in the packet header. And then the driver core picks the stack core. There's a collection of approaches that are possible in Linux for that. And then finally, the Linux scheduler picks where the application is going to run. And so the problem is, oh, by the way, in TCP, packets, all the packets in a flow have to traverse exactly the same set of cores, because if they didn't, again, you could have reordering that would happen. So once you've picked this for a flow, it's stuck. For the lifetime of the flow, all the packets are going to go the same path. And then the question is, well, what happens if, say, some other flow happens to randomly decide on the same core for running the stack software? And the answer is now you have a hotspot. And so that can result in huge slowdowns, big latencies. And by the way, I've measured this in Linux both for TCP and also for Homa. And this problem is, this is the dominant source of tail latency, of software-induced tail latency. A lot of tail latency comes from software, and this is what causes it, because you get one core that's just super overloaded, and everything backs up behind that core. All right, that's my litany of problems with TCP. Any residual questions or comments about that? We'll talk about what we do about it. All right, so we need to kind of work through the stage of breathing here. And I think you have to realize that, in my opinion, TCP is beyond, can't be fixed. Now, people have been trying for 20 or 30 years, but people have identified individual problems, congestion control, and they propose solutions that make those a little bit better, typically not much better, enough better to get a paper at a conference, PhD dissertations and faculty jobs, and but there's just too many problems. And the problems, they're not superficial. They're fundamental to the way TCP works, and they're all interrelated. So, for example, the fact that you don't know about messages makes so many other things hard. But people say, well, okay, yeah, I know it has problems, but let's keep the good parts and just replace the bad parts. And my answer is, can you show me a good part? As far as I can tell, there are no good parts. They say, wait. I mean, we have all these applications that are written to the API. Let's at least keep the API and then fill in everything underneath the API. So the problem is, the API is part of the problem. The fact that it's these byte streams and connections, that's what causes a lot of the problems. There literally is no part worth keeping. So if we want to have a good protocol, a good transport protocol, if we want to really be able to take advantage of this amazing networking hardware that we have in data centers, we need a new protocol, and it basically has to be different in every single respect from TCP. Every place TCP went right, you got to go left, and vice versa. And so I have a proposal for that. You probably knew this was coming, which is Homa. So Homa is we were experiencing problems actually partly with TCP, but partly actually with InfiniBand, which has many of TCP's problems as well, building this storage system called RAM Cloud. And so we just stepped back and said, well, what if we could just design a new protocol from scratch? So no constraints, clean slate redesign. What would that be? And that's what Homa is. It was Benon Montessori's PhD dissertation. And I believe it solves all of TCP's problems by basically being different in every way. So I'll give you a really quick tour. I'm not going to give a full explanation of Homa, but I'll give you a quick tour of the ways in which it's different. So first and foremost, Homa is based on messages, not a string. And so what that means is that messages are the dispatchable units. I need to get a whole message before I can actually do anything. And so now the protocol knows about those. And that's a bunch of advantages. It means we can do load balancing more efficiently. So for example, it's safe for multiple threads to read concurrently from a single socket, because Homa will collect full messages and it'll pass a thread a full message, not a part of the message. And in the future, if Homa is implemented on NICs, that means the NIC can do the same thing and it can dispatch messages, full messages, directly to threads, bypass the operating system kernel completely. So it will work much better in a kernel bypass mode with the transport protocol in the NIC. And by the way, the fact that we have message boundaries means we can do run completion, because we know when we're complete. And we can do SRPT, because we know how large each message is, so we can prioritize the shorter messages.
Question?
Yeah.
How large are messages in this?
How large are messages? Right now, there's a limit of 1 megabyte on messages. That's an artificial number. I have no idea if that's a good number or a bad number. Second thing, Homa is connectionless. There are no connections in Homa. In Homa, the fundamental unit is a remote procedure call, RPC. And that consists of 2 messages. It consists of a request message that's sent from a client to a server, and then a response message that's returned from the server back to the client. And so clients, they launch a request, they get back a response. Servers, they wait for incoming requests and they send responses. RPCs are independent. So there's no response to the question earlier on. At Homa, there's no ordering guarantees between RPCs. If you care about the order, then you implement it yourself at a higher level. It's actually pretty easy to do that, but that is some extra work you would have to do at Homa. And there's no long-lived connection state. Homa only has state for the lifetime of an RPC. Once it completes, Homa does not need to keep around any state for that. I will say that Homa does have some state. Each peer keeps a little bit of state for each other peer. So peer-to-peer state, but that's independent of how many connections or RPCs there are between the peers. And it's pretty small. It's about 200 bytes. And I think 150 of it, I think, is basically the routing table information, which you have to have in any case. So there's no connection setup overhead because there's no connections. And you can use a single socket at Homa to communicate with any number of peers. You can have many RPCs outstanding on one socket at the same time. Responses can come back in any order. You can wait for them. Even so, even without connections, though, Homa still ensures end-to-end RPC reliability. It can handle lost packets and retransmit and do all the kinds of things you would expect. One way of thinking about this is, in truth, Homa, you can think of Homa, it does have connections. It's just they're extremely lightweight and very short-lived. Connection is just the state needed to handle a particular RPC. There's no separate setup phase. The connection is created when you initiate the RPC and then it ends when the RPC is complete. So there's no additional packets or overhead for it. Third, congestion control. I mentioned previously that TCP in most protocols, they control congestion from the sender. Homa does it from the receiver. Since we have to be different from TCP in every respect, this is actually quite a bit better. So the way this works is that if a sender wants to send a message, it can actually send a couple of packets for the message in what's called unscheduled form. It could just launch those without permission. But then after that, after those first few packets, it's not allowed to transmit anything more until it gets grants from the receiver. So the receiver will authorize the transmission of other packets, and it can basically pace those packets. And the idea is that the number of unscheduled packets is just enough to cover the round trip time. So by the time, in the unloaded case, we want to be able to send flat out network speed. By the time the sender has sent its last unscheduled packet, it's gotten its first grant back from the receiver, assuming we're unloaded, so we can run at full network speed. But the receiver does not have to send grants right away. It can delay them. First, if it detects congestion, which it can tell if it's got a whole bunch of incoming messages from several different senders, it knows that buffers are building up in the network switch. So then it can scale back rate of sending grants in order to clear up that congestion. And also the receiver can prioritize shorter messages. This is a technique for implementing SRPT. Yeah.
What does the grant look like? Is it saying, hey, I want a message at most this length? That's all I can handle right now.
Yeah, one of the questions is, what is a grant? Like a grant says, for this RPC, you may send me all of the bytes up to a given offset. And by the way, as you're going to hear later, and here's the priority you should use for sending those as well.
On the previous one about the connectionless thing, how does it compare with UDP?
How does it compare? How does Homa's connections compare with UDP? The difference is that UDP has no reliability guarantees and no congestion control as well. So UDP is I guess you could say it's even more connectionless than Homa is, but it gives up a lot of important properties.
So going back to your first point, the first property, you're kind of putting the burden of ordering now on the application, right? Because now you don't have any ordering guarantees.
Comment is, without the ordering guarantees, we're now putting that burden on the application. Yes, in the cases where you care about it, but again, for most purposes in most data center applications, the ordering is already determined. You don't send RPCs out of order. You typically don't send multiple RPCs where you need them to be processed in a particular order. If you send several requests concurrently, normally you're happy with those completing in any order.
Well, I'm thinking of like if you had a really huge message,
right?
And so let's say you have to do pagination.
Yeah, what about a really big message that's longer than an RPC?
Yeah.
Then you would have to, in
Yeah.
fact, you have to add your own ordering, which again, I'm going to argue, so that is additional complexity, but I'm going to argue that's actually pretty easy to do. And it's a layer you can easily implement on top of Homa. Here and then back.
Within the message, there's an ordering guarantee of packets, right?
Comment is within the message is an ordering guarantee. Yeah, that's right. When you send a message, which is n bytes, those bytes will be presented as a message with the same bytes in the same order on the other end. So Homa guarantees ordering within a message.
So for that, does it require path, like a stable path?
So does that require a stable path? As you'll see later on, no, it does not. Okay. The ordering of packets, Homa is perfectly happy with out of order packets. Question about that?
What's the encryption story with this? We're connectionless. So do you have to do like a key exchange every time you send a message?
What's the encryption story with Homa? Right now, there is no encryption story with Homa. It doesn't do it. That's left to the application. So I would assume that you would want to do your key exchange at a higher level, like application to application. And then you'd encrypt all of the messages for one destination application using the key for that.
Thank you.
At some point, Homa will need probably want to have encryption built into the protocol at some point. It's not there right now. Let's see. Okay, so on the congestion control, so the cool thing about having message lengths is that they allow us to predict the future. This is really powerful when you want to do congestion control. As soon as a receiver gets the first packet of a message, it knows how long the message is. And so it knows exactly how many bytes are coming. So it knows it's going to be getting a lot of data up to that point, and it knows exactly when the data is going to stop. So that gives you allows you to respond to congestion faster and much more accurately. Whereas with TCP, it's kind of sensing, it kind of feels like there's a buffer building up over here. I better do something. But maybe, in fact, all the packets have already been sent. This is as full as the buffer's ever going to get. But TCP doesn't know, so it scales back. And then it ends up delaying packets when it didn't need to. Or you don't know when the message is going to end, so you stay really conservative until finally you start realizing, oh, I'm not getting congestion warnings from the network anymore. I can ramp up my sending a bit. So it's just much more difficult to do really rapid, accurate congestion control when you use the buffer occupancy as your signal for that.
So about the grants, right? How does the receiver know if there is congestion in the network? It just knows it's going to receive this many packets. Does it just make a guess that it's getting a lot of those headers initially, so it's sending? Because if it can process, let's say it's getting 1 million messages and it knows it can process 1 million messages, but that still might be congestion in the network, right? So it cannot detect whether there's congestion in the network.
The question is, how does the receiver know that there's congestion? So Homa can't detect congestion in the fabric.
Yeah.
So we're talking just the downlink between the Tor and the host. And so if I see that there are several large messages incoming, I know that my downlink is going to be overloaded.
Sure. Okay.
And so I can pace the grants, at a rate that I know is about the rate that my link can sustain.
Okay. And do all the intermediate nodes also implement this? Like they don't, right?
Intermediate loads of the fabric. Also
Because they're on
I'll come
based
back
on
and talk about that in a second. I believe that there's no need for there ever to be congestion in the fabric.
Okay.
Question from behind you, yeah.
Oh yeah, so that if there are multiple senders and one receiver, it's possible that the scheduled packets might get blocked behind the unscheduled packets, right? At the receiver end?
The question is, there's multiple senders and one receiver. Could scheduled packets get blocked behind unscheduled packets? They could, yes, potentially. But typically there aren't very many unscheduled packets, and those will get out of the way pretty quickly. So if you have a bunch of large messages coming in, you'll very quickly everything will be granted. And so you don't have to worry about that. And also, I don't have time to explain this in detail, but Homa uses the priority queues and switches, a feature that was not available when TCP was designed, so it doesn't use them. And it can use that also to allow, for example, short messages to always get through and never block behind long messages. So anyhow, the message length is really great. Like I said, you can predict the future. As we know, all the best scheduling algorithms for anything require you to predict the future. It's fundamental of the scheduling. Of course, you almost never can. Fourth difference, as I mentioned, TCP does fair scheduling. Homa does SRPT, and it does that in two ways to try and prioritize short messages. One is by controlling the grants. And the second thing is that it uses the priority queues in modern switches. They typically have 8 or 16 priority queues at each egress port, and you can add a priority to a packet that determines which queue it goes into. I'm not going to go over the details of that mechanism, but this works. Homa is able to use those queues quite effectively to make sure that short messages virtually never wait behind long messages, even when in situations where there is fairly significant queuing. Only the long messages conducted the long queues. And so I had a graph earlier where I showed you, this was TCP in green and DCTCP in brown. This adds blue to that to show you, first of all, Homa's latencies, notice, are just way lower. By the way, these are all running on Linux. This is a cluster of 40 nodes running on this 25 gigabit networks. So Homa's latency is almost 10x less than DCTCP and more than 20x better than TCP. And furthermore, people often think, but if you're doing SRPT, isn't that going to prejudice against the long messages and they're going to really suffer? Doesn't appear to be the case. Even the longest messages is about a factor of 2 better tail latency for Homa and TCP. And that's because of run to completion. It turns out that this run to completion improves performance at every message length, particularly short ones, but even in long messages. You can see this rise here. That's SRPT kicking in. So you can see as the messages get longer, in fact, their slowdown does increase. But even so, you're better off with Homa than with either of the two TCP variants.
My understanding is that for TCP, because it is a socket-based thing, your PFC's priority flow control, that is priority queues, don't adhere to the shorter messages being unblocked by longer messages. But for Homa, that information is passed down to priority flow control.
Yeah, the comments about TCP, you talked about using priority flow control. First of all, TCP does not use that. PFC is typically done, that's used for different things.
Correct, but you could
for InfiniBand.
Right.
But the problem is that TCP does not use the priority queues in the switches.
Right, but you could do it with TCP as well.
So you could with TCP. It's typically done on a per flow basis, though. You have to associate the priorities with byte streams, and that's not the right way to do it because, again, different messages you want to use different priorities for. But with TCP, everything has to be done for the stream. It's just the wrong unit.
What's going on with the 50K? Like, why is it faster than the smaller messages?
Why is it this drop? So first you have to remember this is slowdown. So it's how much slower does it get compared to what it would be on an unloaded network? How much slower does it get under load? So the absolute times here will be much higher. But the thing is, the base time is already much higher, and it doesn't slow down as much when the network gets slower. Moving on, the last issue. So Homa has no ordering requirements, so it does not depend on in-order packet delivery, and that means you can use packet spraying in data center networks. So blast the different packets for a message across the fabric. And I believe, my hypothesis is this will completely eliminate any sort of congestion issues in the network core. Unless the entire core is systemically overloaded. And all of the data I've seen suggests nobody will run their core like that. That causes so many problems and causes, basically, it will waste all of your cycles of the machines stuck behind the network. It's just not cost effective to do that. In fact, my understanding is that the cores tend to be systemically underloaded. We're running sort of 10 to 20% loads. And the problem is with TCP, even at those low loads, they get congestion. Homa, I believe, get no congestion that way. And then, by the way, we can also do better load balancing across the cores in a machine. I had to, in the implementation of Homa and Linux, I had to go to a lot of work to defeat the way Linux wanted to schedule things, which was to do this flow consistent scheduling. But I was able to figure out ways to do that. So again, I can do better load balancing in software as well as in hardware. Okay, so now the question is, well, suppose we have a better protocol. Could we actually replace TCP? Well, probably replace is not quite the right word. It sort of takes some of TCP's traffic. TCP is not going to go away. And there's a lot of things for which people use TCP where TCP is fine. But for the applications that really want to take advantage of the data center networks, how can we do that? Well, the first step is we have to have a good implementation of Homa. And when Benon finished his dissertation and went off to work at Google, I decided to make this my mission in life. Because the results we got from the early simulations and measurement were so great, just really some of the best results I've ever seen in a PhD dissertation in my career. It would be crazy to just let this idea become a paper that then dies. So for the last, 4 or 5 years, it's been my personal goal to do whatever it takes to either make Homa displace some of TCP or learn why that can't possibly ever happen. If I ever get to that point, then I'll give up. So the first step is a good implementation. So I built a Linux kernel module for Homa. It's available in open source form, the paper on it, easy to download and use, there are any kernel modifications. And the graph I showed you earlier was based on that. And the performance improvements are pretty amazing across a variety of workloads. At the median, Homa for short messages is sort of 3 to 7 or 8 times faster than TCP. And at the tail, it's anywhere from 7 to 72 times faster. So huge performance differences. And over the last couple of months, I've started upstreaming this into the Linux kernel. So there's a first patch series that's undergoing the brutal beating that any patch series always undergoes before it gets into the Linux kernel. We're actually working through that. So it'll take some time to get it into the kernel, but I expect that to happen over the next, months or year or so. The bigger question is, how do we get applications to use Homa? And I'm pretty clear-eyed about this. If there is a more deeply entrenched standard anywhere in the world than TCP, I'd like to hear about it. So it's going to be hard to get applications to move off TCP. I understand that, particularly because Homa's API is incompatible with TCP. So we can't just slide Homa in underneath TCP applications. And I recognize, there's millions of TCP applications out there. There's no way most of them will ever get rewritten. Most of them don't need Homa anyhow. They're designed for a different world. Maybe they're just streaming data. They don't care about latency. But for the applications where Homa could benefit, so my first thought, this is my plan A, was to leverage RPC frameworks. If you look at today's data center applications, they don't typically code directly to the Linux sockets interface. They typically use some framework for doing RPCs for reasons I've talked about. For example, with sockets, you don't get the reliability model, for example. And there aren't really many of those frameworks. There's gRPC and Thrift and maybe a few others. So I thought if we just add Homa support to the frameworks, then it should be trivial to convert the applications, like a command line, argument. You say just use Homa instead of TCP. Bingo, one line change and you're running with Homa. So with that thought in mind, I bit the bullet and I added Homa support to gRPC. At least gRPC has a couple of different versions. It's really only the C++ version that I've added it to so far. But gRPC is slow. In fact, I am at a loss to come up with the right adjective to describe how slow gRPC is. It's just unbelievably slow. So here's some measurements for, this is for short RPCs, a few hundred byte RPCs. You know, if you just use like the raw TCP or Homa, you can do a round trip in about 30 microseconds with TCP. Actually, a little better than that if you're just using raw TCP, and 15 to 20 microseconds with Homa. With gRPC, with TCP, it's hard to say this without crying. It's 90 microseconds. There's 30 microseconds of extra overhead on the client, on each of client and server for the simplest RPC. What value is gRPC adding for, that's roughly, was that 30 million instructions it's executed? I forget. It's some huge number of instructions it's executing. What is it doing? The answer is it's just going through layer after layer after layer of procedure call. Procedure A calling another method as essentially the same name as A, another method with the same name as A, the same name as A, and do this about 10 times, and then it calls B, and then another one with the same name as B. It's just basically doing a lot of procedure calls. So, you know, Homa made things a little bit better. It's sort of interesting, just the overheads in Homa are lower than those for TCP. But the number is already so high that we'd like to do round trips in, again, 5 to 10 microseconds would be the goal. It's going to be really hard to get there ever with gRPC. And I went to the gRPC developers conference one year and I asked around, and honestly, there just wasn't much concern in the community about performance. People just don't care. It doesn't, for the things they're building with it, I guess the performance that it provides is adequate. So there's really no motivation there. I decided pursuing that probably doesn't make sense because nobody in that community will care. Homa won't provide that much value for them. Then I started wondering, is there some other RPC framework? And I asked people about Thrift, and people said, this might have the same problems as gRPC. I don't know if that's true or not. So I'm curious if anybody knows of an RPC framework that internally has really, really low overheads. It's adding, say, 1 or 2 microseconds of overhead, not 60 microseconds of overhead. And where the users actually care about latency, then that would be a great target, but I don't know of one yet. So I've switched to plan B. Plan B is first find areas where people really care about latency, and then see what we can do to accelerate those areas. And I think the most attractive target I've heard of so far is storage systems. People really do care about performance in storage systems. And so suppose we were to add home support for Homa to some widely used storage systems, then this is another example where the applications don't program the sockets, they use the API for the storage system. And so it should be really easy to convert the applications over. And I think the best place to start is Redis. I think that's the right place to start. I have not had a chance to get to this yet. It's on my list to do, but that's my next plan once I get some free time. If anybody out there is interested in this or would like to undertake doing a Redis port, that would be super cool. I'd love to see that happen. So that's where we are. And just to wrap up, I'll be happy to take any other questions you have. Kudos to the people who built data center networks. Really, the networks are awesome. They're really great networks. Unfortunately, TCP is not a good match to them. And so it throws away much of the potential. You know, TCP can use a significant fraction of the bandwidth. It can't take advantage of any of the latency or small message throughput stuff that the networks offer. So the question is, do we want applications to be able to use that stuff? Are we okay just letting that potential performance get flushed down the drain? If we want to actually get that, reflect that through to apps, gotta do something besides TCP. So if it's not Homa, then your good idea goes here. Homa, I put that up as a target because I think it pretty much solves all the problems with TCP. And then again, the biggest challenge once we have it is how do we, this is a problem with all new technologies. When you come up with a new technology, you can have a great idea, but if there isn't some way to somehow get that idea adopted, then it can't go anywhere. So I think that's the challenge for Homa. How do we get it adopted? If you have any other ideas besides the ones I thought of, I'd love to hear them. So with that, I'll stop. Thank you, and I'm happy to take more questions.